The topic of this presentation is the effective assessment of welded structures. After starting the limit GUI, the first step usually is to import the finite element model, and that's what I'm going to do. We are looking at an Abaqus input, so I will select the Abaqus preference. I have to work my way through the file browser, and I will select the finite element input. So what you see here on the viewport is a shell model of a welded structure. We have the possibility to color code the elements according to their properties. So what you can see here in different colors are different shell property definitions, and we can go through the model data tree to highlight the different areas with different thicknesses, or at least different thickness definitions. Now, to give you an idea how this structure is loaded, I have this picture here that shows the deformation and stresses for the structure. The structure moves up and down, and these vertical accelerations, in addition to the gravity load, cause bending moments acting on this cantilever part, and furthermore causing local bending stresses here at the flange, between this flange plate and this larger flange plate welded to the larger part of the structure. The deflections are scaled by a factor of 300, but still one gets a pretty good idea what happens around the flange. And also typical for these structures is that we have high stresses in a very local area, and larger portions of the model show rather low stresses. So if we return to the limit GUI, the question arises, how can we make an effective fatigue assessment of the complete structure? This structure consists of maybe 20 different plates, but still we would have to define like 50 individual welds for a fatigue assessment. But the more efficient way is to do the assessment in two steps. In the first step, we would like to identify areas which are highly loaded, and in the second step, we would make a detailed weld analysis of the higher loaded areas. Now, Limit has two different possibilities to analyze welds. One is a global approach where we use the stresses calculated on the bottom and top side of the shells, and we compare these stresses to the permissible stresses given in different codes. So this is the global approach, where we don't really calculate the stresses in the local welds and fillet dimensions. And in the second assessment mode, which is called weld, we can take a detailed look into the local welding condition. We can define the orientation of the weld, we can define the local geometry of the weld, and calculate stresses for toes and roots, and make a really detailed fatigue assessment of the weld. Now, naturally, we have to put more information in the model for the detailed analysis, but this we only want to do in areas which really are highly loaded. Otherwise, we would waste time. So, in the first approach, we want to make a global analysis, and if you look at the limit menu, you see different topics beginning with file sets, sensors, loads, setups, and jobs. Usually you work your way from left to right, and topics that are not used very often have been moved far to the right. So usually you begin with the file import and you end with the jobs, and additional possibilities and functions are moved even further to the right. Now we have imported the finite element model already, so the next step is actually to define which elements should be analyzed in this fatigue assessment. For limit, it's always important to define an element set, because the fatigue assessment is always performed for a special element set. Now, if we talk about a welded structure, every part or every area where different shell properties meet are potential welding areas, and using the information on the shell properties, we can automatically derive these element sets from the structure. So within the sets option, we can select the function generate weld sets by properties, and the program runs through all the different property definitions and looks if elements with different properties share nodes, and this way we can detect all potential elements near welds. Now, if I mark the overall set where all elements are included, all potential weld elements are included, you can see highlighted these elements, and naturally each weld itself also is stored in a separate set. So we could look at the set number 20, for example. If I zoom in a bit, you can see the node row, which gives the orientation of the weld, and we can see highlighted the two element strips that are connected to this row of nodes, and for which the fatigue assessment analysis will be performed. Okay, so we have defined node sets. We have one overall set which we can use for the global weld assessment, and after that we can take a close look at the locally highest loaded weld, and in this case we can use these local weld sets. So we can actually complete the topic sets and move to the next important issue towards the jobs. The next point would be sensors, but sensors is a technology that is only used for the weld assessments of structures that were modeled as continuum elements. So with the sensors we can use 3D continuum elements in models and do detailed weld assessment on the basis of these models. We don't need sensors in combination with shell element modeling. So the next important step are the loads. I will open the load manager, and what you can see here are 3 different fields where we can define data. Limit imports in the first step finite element results. So that's what I'm going to do here. I'm going to define which finite element results I want to use. The ODB from which I'm going to read the stress data includes 2 finite element steps. So I define 2 finite element results. One I will call step 1, and the stresses should be taken from the actual step 1 in the ODB. And I will create a second one, call it step 2, and this data case should be imported as stresses from the step 2 from the ODB. If I don't define any increment numbers, then the program will take the last increment of each step. Now the name you can see here, step 1 and step 2, is only a limit internal name. It has nothing to do with names given to steps or load cases in the finite element analysis. The only way to identify steps or stress data in a finite element result file is via the step number and the increment number. Now, once I've defined the finite element results I want to read, I can use these finite element results to calculate or derive loads or stress data that I can actually use for the fatigue analysis. Now in this case, I want to use these FA results as they are, so I can create loads directly from the FA results. And what you can see here means that the finite element results from step 1 are taken directly with a factor of 1.0, and the name of this load set is load underline step 1. The basic idea is that we could also import a larger number of base state stresses, and perform linear combinations to build up complex loading conditions and situations. So this superposition can be performed within limits, which saves storage and CPU time. Now, additionally, I would like to define a third load case, actually a trivial result with all 0 data for stresses. So what I will do is I will just copy an existing load, and I will set the weighing factor to 0. This is one simple way to create a load case with all zeros. Actually, this load step, this additional one, is not really physical, but I've just introduced this step to increase the possible stress range, just to have more to talk about in the post-processing. Now, what will the program do? The program will start a fatigue analysis in a local coordinate system. This could be the coordinate system of the weld or an element coordinate system, and it will search for the largest and smallest stress for each component, and this will give us the stress range for each component, and with the stress range we can calculate the degree of utilization. So as in the moment we don't need any further information for the load manager for this simple presentation. So with dismiss, I close the load manager, and the next step is to define a setup. In the setup, we define which element sets should be analyzed according to which code. So what we do is we create a setup, and we can rename the setup. In this case, I will call it Eurocode 3 underline weld global. And limit offers three different assignments, or three different calculation modes if you want. The first one is a mode for base material analysis. The second one is weld global, which actually is a first hopefully conservative approach where we use the finite element stresses for the shells and directly calculate the degrees of utilization according to conservative FAT values. And in this case, we cannot take into account the local orientation of the weld, and we cannot take into account the geometry of the weld, but we just use the shell stresses for a global approach. And in the more accurate mode, which is called weld, we can define the weld geometry, the weld orientation, and define different FAT classes for toes and roots. And with that option, we can make a really detailed fatigue analysis. But since we don't really know which areas are highly loaded, we will start with the weld global analysis. Now, next step is to select a code. In this case, I will use the Eurocode 3. All other data can stay in the default values. I will select the set I want to use, which is the PS all 01, and to finish I have to at least give a yield stress. I could define the partial safety factor for fatigue load intensity and the partial factor for the fatigue strength. I will set these values or leave these values at 1, and here I can define the FAT classes or FAT data I want to use on the bottom and top surface of the shell in order to make a fatigue analysis. In this case, I will take the lowest FAT value, which is 36, and P1 or P5 is the lower or bottom surface, and P6 is the assessment point on the top surface. If you push the help weld button, this little sketch pops up, which shows you what the different positions P1 to P6 mean. In the case of using the stresses directly on the shell bottom or top surface, P5 and P6 are involved. If we want to make a detailed analysis of welds, then additionally P1, P2, P3, P4 are activated, and the user can define FAT classes for each position, and will also get results for each position after the analysis. So here the 36 is enough to define the fatigue data. Limit will search in an increment of 15 degrees the most critical loading direction in an element, and it will calculate the largest stress range and give a degree of utilization for this combination. Okay, with apply I can close this, and we have our setup. And the last thing I have to do is I have to define a job. I push the create button, job 1, underline Eurocode 3, weld global, apply, and now here I can select the preference, which means I have to select the finite element interface I want to use. In this case it's an Abacus 612 interface, which is already selected, so I can use this. I have to select a result file, which is an ODB in this case. I'm looking for a hookup .odb, and then I have to select my setup, and I have to select some loads, and with apply I can close the job manager. And as a last step I can run the job, and what I can see here is an echo to this window. You can see that the analysis actually is already finished, and the program is in the phase of writing the result files, and in the meantime it has finished. Now here I can mark my job, and when I push the view result button, the viewer module opens, and we can go into the post-processing. Now this is very similar to the limit GUI, and you can see the structure in the viewport, and you have a list of results. The DOU means degree of utilization, and there is a result type max degree of utilization, and if I click on this, then we get the results and color coded, so we can see that, for example, this one element as part of the flange plate has a problem approaching the weld. So actually the weld toe for this element has a utilization ratio above 1, which means that the FAT36 is too conservative for this local situation. And in order to make sure, or in order to find out if this weld really has a problem or not, we would have to go into a more detailed analysis to really get the local fat classes of the weld in a correct way. You can visualize your degrees of utilization for both the top and bottom side, and the maximum degree of utilization is the maximum value for all positions 5 and 6, and you have also the possibility of activating a query function, and you can directly check out the values that are shown here. Additionally to the query function, you also have information on the local FAT values that were used for this weld. So what we have to remember is that we have a highly loaded weld here, and that's the area we want to look at in a more detailed way. So I will close the viewer once more, and I will move back to the preprocessor. Now actually I don't know in which weld set my critical elements can be found. So what I do is I just click on one element. It is highlighted in white, and when I push the right mouse button, then I can select create setup, and if I do so, I have a list of all possible weld sets in which this element is located. We have two. One is PS all and one is PS20. So if I click at PS20, then automatically the setup for this weld is activated, and what you can see here is in a symbol that represents the thickness of the shell, and but still it's not really visible in a perfect way. So what you can do with limit, if you push the space bar, you can activate the transparency mode, and if you push the E button, then all element edges that are not involved in the local weld you want to look at disappear. So in this way, even in complex models, we have a good representation, a good idea on the local welding situation, and can see which parts are joined at this point. Okay, so the next step is we want to perform a weld analysis, which is a local fatigue analysis. We want to use the Eurocode 3. We have already selected the correct element sets we need. We have two different element sets, the blue one and the green one. The green one is actually the continuous sheet, and the blue one is welded to the green one. Yeah. So what do I have to do? I have to define my FAT values, and I have to define the dimensions of my weld. Now, as I already said, the blue part is welded to the green shells. So all section forces and moments that are carried through the blue elements have to be transmitted through the weld section itself. So in this case, I define, for example, a one-sided fillet weld with 5 millimeters cross section, throat dimension, and the symbol of the weld is shown here on the viewport, and the user can check and has an immediate feedback whether the side from which the weld was positioned is the correct one. What you can see here are the different welding positions. I again will show you the help weld, which shows the sketch with the different positions. So 1, 2, 3, 4 are assessment points of the weld cross section, and 5 and 6 are assessment points on the bottom and top surface of the shell. So by defining a dimension, which is a fillet dimension of 5 millimeters, I activated two additional assessment points, 3 and 4, for which the fatigue analysis will be performed as well. And in brackets you can see 3 different values. The first value is the FAT class for loading parallel to the weld. The second value is the FAT class for loading perpendicular to the weld, and the third value is the FAT class for loading, for shear loading. Again, we have to define the yield stress. I won't check the FAT values because these default settings are okay for our purpose. The only thing here is that if we look at this detail here, then the continuous sheet is only welded from this side, and on the back side we have actually base material. So for the P6 of the green elements, actually there is no FAT class 80 for loading transverse to the weld, but actually it should be a base material or something like a FAT class 100. So if I push the return button, you see an update of the values here in the viewport, and again we immediately can see how which values were changed. Now the position of these symbols can be changed by the user. You can actually switch to the next weld and see how the definition would look like on this detail, and this way you can check all your involved welds. Okay, so for this analysis the default values are okay, and we have all important settings. So with apply I can close this, and we can immediately switch to the job manager. I don't really have to define a new job, I just copy the existing job, call it job 2, and I just have to replace the inputs that have changed. In other words, I just have to select the new setup, and with apply I can close this, and again run job, and the fatigue analysis is performed for this detail. So I mark this again on the start of the viewer. Now we have more result data. We also have data for the assessment position P3, P4, which is root top or toe top welded from the top side. For the first important post-processing step, we will look at the maximum degree of utilization, or maximum degree of utilizations element here, and what we get is this picture here, which shows that the maximum degree of utilization is below, no, it's 4.01, so it's very high, but the area of the maximum degree of utilization has changed from the continuous flange to the elements at the weld, the elements that are also involved in calculating the stresses in the cross section of the weld. So what we actually see here are results that were calculated for the root and for the toe of the single-sided fillet weld, and since limit also takes into account the eccentricity of single-sided welds, which add an additional bending moment. Single or one-sided welds always are dangerous and show rather high degrees of utilization. So we can switch through the data here, and we can see that actually the high degrees of utilization are calculated for the root of the single-sided fillet weld. The toe is much better. It has a degree of utilization of 1.3, and the other points are okay. The P6, also the continuous sheet has degrees of utilization below 1. Now, in order to solve the problem, I can go back into the setup. I can, for example, define a double fillet weld, which can be done here. I just type, let's say, t times 0.5, which means that limit will take half the thickness of the local shell as a dimension for the fillet. And I can define this on all positions, which will give me a double-sided fillet weld, which looks like this. And with apply, I can leave the setup manager and go back to the job manager and just rerun the job. All the data that has changed is updated, and the job is finished, and I can directly look at the results again. And degree of utilization, and now we are fine. Adding the second fillet really reduces the stresses and reduces also the degree of utilizations. And again, the most critical or the highly loaded point is the toe of the continuous sheet. And all my values are below 1, so actually we have a sufficient weld for this web to flange joint, and we could switch to the next critical area of the structure. But I'm done with the presentation at this point. So I was able to give you a short overview of the efficient assessment of welds. In even more complex structures, we would probably end up with detailed weld analysis of several welds, but the big view and the methodology will remain the same. First step, and global assessment, and in the second step, a detailed analysis in areas where we have high stresses and high degrees of utilization. Thanks for your attention.